record. Great. Well, good evening and good morning to some of you. And I'm Wim Ming, and I'm a product manager at AWS AI. So Grace is the evangelist from NVIDIA side. So she and I have been hosting this meeting for quite a while now. I think this is what the 10th meeting, I believe. Grace, do you remember how many times we've been
Our
hosting?
first one was in February.
Oh, February. So this is the 9th one.
Actually, January. No, January.
It was January. So this is exactly the 10th one. So we have seen a lot of presentations from, we've seen some great presentations from a lot of researchers and also industry users of GNNs. And, you know, we've been also looking at different topics. So I think it has been, you know, our user community has also grown from just 200 or 300 to right now almost 900. I think it's more than 900 now. Yeah, it's 925. So I think, you know, we're seeing some great interest and great growth in this area. And of course, you know, we look forward to have this community grow organically over the next year. So we plan to continue to run this user meeting as far as I can foresee. So at least for next year, I even bought a Zoom license for next year. So we also want to thank everybody who participates in this meeting. So tell your friends and tell other folks about it. We also seen people, you know, watching these on our YouTube channels, and I'll try to get the recordings out as soon as possible for every meeting. So we do have one item we want to kind of get everyone's opinion. We actually have the next month's meeting being on the eves of Thanksgiving. So I don't really think, you know, you guys would want to join us instead of your family. I know we're kind of a big family here as well. So we're thinking about skipping next month and resuming on in December. And then December is another holiday. So it's Christmas. So we're mostly thinking about moving that to, you know, December 11th and as our next user meeting. And I'm thinking about, you know, maybe we'll do a celebration. What I will do is I will try to get a budget for some, you know, raffles and gifts. And I think Joe has promised us some hardware at the very beginning. I don't know if he would, I don't want to volunteer him, but so if there's anything we can do from, you know, the marketing side from NVIDIA, so definitely, we should definitely join forces to see if there are things we can bring.
Bring some Christmas presents for the group. Yeah,
that's right. So we'll bring, I mean, and you know, and the second thing is that I intended to have this group being relatively small, so people can ask questions since it's a casual, you know, user group meeting. So I like to keep it, you know, still within, you know, 50 people. So I think it's a very reasonable, you know, size for the community for the live session. And then of course there's, you know, the broader community can, you know, always watch the videos at their leisure. So today we have two talks. The first talk is from Zhen Da. So he is a research scientist, applied scientist on the DGL team. So he's actually based in Palo Alto. And he's going to talk to us about the latest development in large-scale GNN training with DGL. So this is, you know, some of the work that he has been working very closely with NVIDIA teams. I know Dominic is also here, so Dominic is also here. And the second talk is going to be Carl. Carl Yan is going to be talking to us about new trends and results in graph federated learning. This is a very interesting topic that's also trending. in the non-graph neural networks. And then we have, some time for open discussion. So without further ado, I'll have Da come and share his screen and present.
Cool. Yeah. Let me share my screen. Should I? Oh, okay.
Yeah, just click on it and you should be able to share it directly.
Sure. Okay, let me see which desk. Oh, okay, this desk is the right one.
Desktop, yeah.
I might need to exit first because I don't have the permission.
Let me just allow. Yeah, you should be able to share.
No, not that permission. This is a Mac OS.
Oh, Mac
OS.
Mac permission.
I will come back. Sorry about that.
Okay. Yeah, no worries. Yeah, take your time. So I assume that's a file permission that you will have to deal with. Are you able to come back? Got it? Perfect. All right. So Da, you're on mute, I believe.
Okay. Can you hear me?
No, we cannot see the screen anymore, but I can hear you.
Yeah,
So.
it's a little bit difficult for me to set it up.
Okay, perfect. Now you got it.
Now it works.
Take it away.
Now it works. Okay, cool. Okay. Again, thank you very much for inviting me to this meetup. And today I'm going to talk about the latest development of distributed GAN training in DGL. So my name is Da Zhen. I'm a senior applied scientist in the DGL team. So as we know that graph has been used in many applications, and we want to generate the business values from those graph data. And to do that, we would like to apply graph machine learning techniques on this data. So for example, we may want in the social network, we would like to apply graph machine learning to identify influencers and bad actors or moderate content. And in the e-commerce, we would like to apply graph machine learning for recommendation, product ranking, and so on. And in the case of knowledge graph, we also like to use graph ML for identifying missing information and answer questions, something like that. And in all those applications, I mean, we need to process a graph with billions of nodes. And since this is more like a GAN meetup, right? So I mean, we know that people GAN now is becoming a very popular technique for graph machine learning, and we have seen the popularity of graph neural network growth significantly in the past few years, and in both the research community and also in the industry. And we have seen the researchers are applying this technique to many applications, and we are seeing a very promising result. Now the main question is, how are we going to apply graph neural network on on the graph that is in the billion scale. So this is still is a one of the biggest challenge for us to applying graph neural network on those applications, as far as I know. So one potential way of performing graph neural network training on those data sets is we can do like a full graph training. This means that we need to perform graph computation on the entire graph data set during the training. In this case, we will just take the adjacency matrix of the graph and apply a new, then we apply a neural network function f to the to the input node features and adjacency matrix for each for a single layer GN, or for multi-layer GN, we will just need to apply another function g on the output of f and sorry, I don't know, let me restart. So for multi-layer GN, we need to apply another function g on the output of f and the adjacency matrix again. So in the case of full graph training, we need to apply both f and g on the same adjacency matrix for this multi-layer GN. But the problem is this method will consume a lot of training. This training method will consume a lot of memory, and this memory consumption is proportional to the number of nodes and the number of edges. In this case, if we really want to try this method on a graph with like billions of nodes or and many billions of edges, we probably need to consume like terabytes, many terabytes of data, and so we can run out of memory very easily. And also, we tried actually digital team actually experiment by really doing the full graph training on the large data set, and we found that the convergence of full graph training is much slower than mini batch training, and it can be as like 100 times slower. So, and also we noticed the full graph training sometimes gets lower model accuracy. So therefore, we still need to perform mini batch training for graph neural network, just like what we do for other deep learning models. Now, the main question is, how are we going to apply mini batch training on graph neural networks? So the main difference is that unlike the other deep learning models, like the data in a graph has dependencies. Basically, nodes are connected with edges. So therefore, we can no longer sample data from a graph in an IID fashion, just like what we do on the other deep learning models. So the one potential way of sampling mini batch from a large graph usually involves 2 steps. And in the case of, this steps might be a little bit different for different tasks in graph machine learning application. So for node classification, we usually first need to sample the target nodes from the training set where our model will make prediction. Then we sample neighbors of the target nodes. For multi-layer GN, we need to sample neighbors multiple hops away to construct a mini batch. And in DGL, this mini batch sampling algorithm actually is the one we are using, commonly using. And when we try to apply a scale to distributed training, and this is the mini batch sampling algorithm we are using, and we are trying to optimize. So by using this sampling mini batch sampling algorithm, and the mini batch training will become like this. So after we sample the mini batch, after we sample the neighbors, multi-hop neighbors, and then we store them in separate adjacency matrix for each hop. And when we apply, perform GN computation on mini batches, then the computation itself is still more or less the same as before, as we do for the full graph training. So the main difference is that now the main difference is that the adjacency matrices in different layers are now become different. So for example, in this 2-layer GN, we first performed the computation on the second layer, perform the computation on the adjacency matrix of the second layer, and then we perform the computation on the adjacency matrix of the first layer, and which will generate the final output for the prediction. And then based on this mini batch training strategy, we develop a distributed mini batch training in DGL. We call this DGL. And so far, we developed 2 versions of this DGL. So the first version was released last August in DGL 0.6. And this that version was optimized for distributed CPU training. And then later on, we continue improving and extend that implementation and extend that design and optimize this DGL for mixed CPU and GPU training. Now, this version is actually still in the stage of prototyping, but I in this talk actually will mainly talk about the second version. So in the following talk, I will try to refer to the first version optimized for CPU as the DGL v1, and then refer to the second version, refer to the version for GPU as the DGL v2. And in both, for both versions, the overall design is more or less the same. So in the DGL, all the machines will have the same function to parallelize the training computation. So we will, overall, there are 4 components in this DGL. So we have the training components. That is basically after we get a mini batch of the data, we perform the forward computation and the backward computation to estimate the gradient of the model parameters. And then we have this sampling component that try to sample a mini batch from a cluster of machines to generate a mini batch for the training component. And we also have a storage component that basically is a KV store that stores the node features and edge features of the entire graph. And of course, in the end, and then the 4th component is like more like parameter server or like all reduced function in PyTorch that is trying to estimate, collect all the gradients from all the trainers and estimates, and then update the model, the entire model parameters. And before we perform mini batch training, we need first to split a large graph into partitions. And in DGL, or in this DGL, we use a very lightweight version of MITIS to assign nodes to partitions with minimum edge count. So in this way, we try to reduce the network communication during the training. So after we assign nodes to partitions, then we split the graph into physical partitions and then duplicate some of the nodes. We call those nodes hollow nodes in multiple partitions to speed up distributed training. And also try to achieve a good load balancing during the training. We deploy a few balancing criteria during the graph partitioning. So we try to balance the number of nodes of each edge type. And we also try to balance the in degree of nodes for each node type. So the second criteria basically is trying to balance the number of edges in each partition. And so since the release of the first version, many people ask, or many people have the concern that, okay, MITIS actually has, they have a concern about the overhead and the scalability of MITIS. So this is true that, single thread MITIS takes a long time to partition a very large graph, but actually there is a distributed MITIS implementation called PARMITIS that can partition a large graph with multiple machines in parallel. So, recently we studied try to understand the overhead of PARMITIS in distributed training, and we measure the time breakdown in the entire distributed training pipeline for different components. And we use the OGB papers 100M for this experiment which has like 100 million nodes and 3 billion edges. So we can see from this time breakdown, we assume that we perform a graph partitioning for each distributed training run. And this actually is usually the worst case scenario. This usually doesn't happen because after we partition a graph, we will like to perform multiple runs to train models for hyperparameter tuning. And we might also want to use the same graph partition to try different models, right? So even if we want to, even if we need to partition a graph for each distributed training, we can see that parameters actually isn't the most expensive part. Like loading and saving data actually take much more time than parameters. And then depending on your task. So if we want to train on node classification, we can in this data set, the training is very fast because the data set has a very small training set. However, if the training set is much larger, for example, if you want to do link prediction, which use all the edges in the graph as the training set, then training becomes very expensive, just like the number I show here. One epoch for a link prediction takes like 300 minutes. So basically what we see is that parameters, after we use the parameters, the graph partitioning is not really that expensive. And the overhead is well amortized. So after we partition the graph, we can perform distributed training. In the DistDGL v2, we actually specially optimize for mixed CPU and GPU training. In this training setting, we actually store the entire graph structure and all the node features and edge features in CPU memory. And in this way, we can scale to large graph with a small number of machines. And we run a sampler server in CPU on each machine to sample nodes and edges for a mini batch from the local graph partition. And then we run the KV store server in CPU on each machine to serve node features and edge features stored in the local machine. And then when a trainer gets a mini batch, it samples so the trainer will try to use the sampler server to as well as try to a trainer will sample a mini batch subgraph from the local server as well as from the remote server to construct and then it will fetch the required node features and edge features from the KV store from the local machine and the remote machine to construct a mini batch, and then it will send the mini batch data to GPU for the forward computation and backward computation to estimate the model parameters. Because we are using MIDIS partition, so actually when we trainer generate a mini batch, most of the data access actually come from the local machine. So one question is why we want to use the GPU for distributed GM training. So as we know that distributed GM training actually has a large amount of data communication. Because of that, we may not be able to take advantage of the computation power in GPU. And as far as I know, other distributed GM framework, such as Euler or AliGraph, they actually kind of give up using GPU for GM training. So, however, but the graph neural network are still the same as other deep learning frameworks. So they still contain many floating point computation. So in this case, and GPUs are actually well suited for this kind of computation. And because the GPU has a large degree of parallelism and it has also high memory bandwidth. So we really want to take advantage of the GPU to accelerate the GM computation. In a context of a mixed CPU and GPU training, we also need our hardware to have very, very fast CPU to generate mini batch quickly enough to keep up with GPU. So because in our machine usually has only one or two CPU processors and then each CPU needed to serve multiple GPUs. And then sampling mini batch and getting data across network are very expensive. To optimizing for this setting, we are to really take advantage of the GPU computation power. We develop an asynchronous mini batch training pipeline to overlap a mini batch sampling data gathering in CPU with the mini batch computation in GPU. So, for example, when we GPU is performing the mini batch computation for step 0, and the CPU will move on and to sample mini batches and gathering data for the mini batch of step 1. And to really optimizing, to really utilizing all the hardware resources in the cluster, including the network bandwidth, CPU and PCIe bandwidth and GPU, we try to perform the mini batch sampling asynchronously and also the data gathering asynchronously. But during the training, we still perform the gradient reduction synchronously at the end of a mini batch iteration in order to perform synchronous SGD to train the model. Because what we want is from the framework perspective, we want to speed up training without changing the training method. Now we have seen the brief the overview of how this DGL v2 is optimized, and now let's see how well this DGL can actually perform GM training on this in a cluster of GPUs. So we evaluate this DGL on some large public data sets at billion scale. So those data sets are commonly used in benchmarks. To see how well this DGL will perform on different GM models, we pick both homogeneous graphs as well as heterogeneous graphs for evaluation. So first, we compare this DGL v2 with Euler. This is a distributed GM framework from Alibaba. As I said earlier, Euler is more designed for distributed CPU training. So in our experiment, Euler on CPU and on GPU has more or less the training speed, mainly because the parallelization strategy used in Euler is not very suitable for GPU training, because Euler is completely rely on multiprocessing to parallelize a mini batch sampling and mini batch computation. So in comparison, this DGL v2 on GPU is 18 times faster than Euler on GPU on the same hardware with 32 GPUs. We also try to make a comparison between this DGL v2 and this DGL v1. So again, this DGL v1 is already in the official release of DGL. We can see that this DGL v1 actually has pretty good performance on GPU, even though it was designed for distributed CPU training. And depending on the data set and also the model, we can see that running the training the model on GPU can be at least 4 times faster than CPU. In some cases, we can get like 15 times speed up in this DGL v1. And the speed up is higher when the model is more complex. So this is not really surprising because the complex GM models requires more computation, so it can take advantage of the computation power of GPU better. So we also see that this DGL v2 can still get like 2 to 3 times the speed up over this DGL v1 on GPU because of our optimizations that overlap the network communication, CPU computation, and the GPU computation. We further want to test the scalability of our framework. So this DGL v2 gets quite a good speed up on, it actually get better speed up on more complex GM models. So for example, we can get like a 36 times the speed up on GAT when scaling to from 1 GPU to 64 GPU versus 22 times speed up on GraphSage on the same hardware. So when we scale from 32 GPUs to 64 GPUs for RGCN, we get 2 times speed up. So this is like kind of close to linear speed up. So here we can only try, we can only run the RGCN model on this MAG data set because this MAG data set is very, very large. It can only be trained with at least 4 machines. So in summary, we basically develop, I present this DGL framework, and this is a framework really optimized for this distributed GN training and on GPU. And we show that by properly optimizing the framework, we can use the GPU to speed up GN training without changing the training algorithm. And currently, this DGL is still in the stage of prototyping, but I think we will release it in our future release. Thanks. Any questions?
Hey, this is Vikram here. I have 2 questions for you. Can you guys hear me?
I think so, yeah.
Okay. The first question that I have is, I guess there is one fundamental assumption when we do the graph partitioning with metas.
I was talking to a few postdocs about their work, and I got really interested in it. I talked to Dr. Grizzle there. Yeah.
Sorry, who is asking asking a question? It's not very clear actually. That's the voice.
This is sorry. This is Vikram who is asking, but there was a noise in between. So the question that I have is this: doing the graph partitioning, does it affect in any sort of like accuracy in terms of the model? Because graph partitioning basically changes the way the structure of the graph is, and no matter what you do, the way you do the graph partitioning, there is still certain amount of loss in the information. So does it have any downstream effect on the accuracy of the model?
So
Go ahead.
So actually, our graph, the way I should have mentioned it earlier more explicitly. Actually, in this DGL, when we partition the graph, we actually keep all the edges, right? So then when we generate a mini batch, we actually the mini batch, the result of this, the resulting mini batch that it can sample from a cluster of machines will be actually the same as we sample this mini batch from a local machine. In a single machine. So basically, we are not cutting any edge. We just split the graph, and then it does not affect the mini batch sampling algorithm or the training algorithm. Okay.
The second question that I have is about the overlapped computation, where you have the asynchronous read operation versus the computation operation. Are you able to overlap it completely, or does the computation become smaller compared to the data loading time for the gather operation over here?
So first, I think this overlap, the figure of illustration is actually a simplified version. The actual version is much more complex. It's we actually break them into many stages, not just the 2 stages, and then we try to overlap all the stages. Now the question is whether or not we can perfectly overlap everything. It's probably not. Depend on the model. Like if for example, if your graph is, if this is a GraphSage, right? The computation in the mini batch is very small. Then the sampling computation might still dominate, right? And if this is a GAT, then maybe the sampling, the computation in the GPU is much more, it's much heavier. Then the sampling we can hide the entire sampling overhead from the mini batch computation to the training.
Okay.
Yeah.
Okay. Thanks.
Here's another question. I think Locke raised his hand. Maybe you can ask the question. Yeah.
Yeah. So may you go to your results slide?
Sure. Which one? This one?
Yes. What's the baseline and absolute time here? So all you have is normalized speed up here, but how long in absolute like seconds does this DGL V1 take here?
So you mean in CPU?
Yes.
Yeah, I should put a number. I can not really remember in top of my head, but I checked. So I remember like in for papers 100 M, 1 epoch is very fast. It's like 10 seconds or something. But I mean I'm talking about the DGL V2. So I don't remember exactly what is the exact seconds, but it's in the order of seconds, not in the order of minutes.
Okay. Second question, the mini batch size you're using here, how large is it?
So okay, so that is yeah. So mini batch size, I suppose you mean the mini batch size for in each GPU, right?
Yes.
So typically we just use the 1,000 target nodes as a single mini batch. However, we need to sample neighbors, right? And in this experiment, actually we sample 3 layers of neighbors, and then the fan out is also quite large. It's in the order of 10. So in the end, a mini batch it contains like 100,000 nodes.
Mm-hmm. But for each GPU, say your mini batch size is 1,000. If I had 4 GPUs, this means that each GPU would do a mini batch of 1,000 locally. Is that correct?
Yes.
Okay. And last question, do you have a sense of the breakdown of execution time here? Like how much time is spent in this bar you have here in sampling, in compute, and in communication? Do you have a general sense?
That is very difficult to estimate because everything is overlapped.
Mm-hmm.
Right. I mean, we can do like a synchronous computation and then measure the time each, but then that time may not apply to the asynchronous version, right?
Mm-hmm. Yeah, thank you.
Okay, cool.
So I saw here you're doing a G4 DNs, and I think those are like T4 GPUs. Do you have a sense of what doing like an A100 versus like a G4 here? Like, I'm just curious about the trade-off between small GPUs that might be cheaper versus bigger memory boxes. And
Yeah.
same thing for a multi-GPU.
I think that all the question comes here is here, like what is the GPU here and what is the CPU here, and how much computation power we have in the CPU, and also what is the PCIe link. So I remember, I mean, for first like if we do that same experiment in like a P3, then those instances have very old CPU. And then it's very, very slow. I mean, the CPU part is very slow. So the computation is completely bottlenecked in CPU. So I will say in P3, in the end, the Trinity actually in P3 is slower than in G4. But this is not because GPU is slower, it's because the CPU is slower. And also about the A100. The problem is that, I mean, I think it's like for example, our P4 has A100, right? But I think now the question is still the same question: is the CPU fast enough, or is the PCIe fast enough? I need to look into details of all those hardware aspect to understand.
So maybe just make sure I got it right. So you're saying the CPU ends up being surprisingly important, maybe because of this like push to the CPU and also the async stuff. But then you're not actually as focused on the GPU RAM or the like multi-GPU like the NVLink. Like it's really the CPU to GPU that you're focused on, and the CPU itself.
No, so the communication comes from two directions. two components, right? For gradient exchange, then the gradient exchange will cause a lot of communication. But in our experience, the most of communication comes from CPU to GPU, because we need to read all the node features and edge features from the CPU memory to GPU memory. And yeah.
And related to that, I was actually like something that I found surprised when I saw the load times of about 20 minutes. And was that just because it's just like S3 to the node, or was it like the key value store? It's like when we do things like Parquet or like, you know, Dask QDF and Parquet, like that's normally not as big of a footprint. So I was kind of curious, like, was this pre-processing? Was this like, yeah, like what was going on with the load save stuff?
Okay, then I didn't dive that deep into this part. So the loading time, for example, is basically we have I think maybe one problem here is that for loading, I mean, the operation is actually done on the NFS or EFS in AWS. So we are so loading data means that we are reading data from NFS. So that part is kind of slow. But then question is, how are we going to do this kind of data? I mean, how should we? What kind of storage we need to set up for the pre-processing, and then later on for the Trinity, right? I don't know what kind of storage you are using for Dask.
Yeah, in Dask we would actually do local node, and then we just do peer-to-peer. And so, because it looks like it's for the partitioning, which means I think that with what the terminology there, that's like between partitions, right? I mean, between iterations. And
yeah,
so,
yeah, in that case, then we still need to, find a way to, after we partition the data, we need to load the data to the cluster you want, unless this is the same cluster.
yeah, so I was assuming it was the same cluster. So okay, so this might have been like in a out like a data warehouse or something, just fully separated. Okay.
Yeah, I mean, because in our case, we try to use the CPU machine for the partitioning, and then GPU machines for training.
And maybe just I don't want to take people too much time, much more on this. And then when you're doing that transfer, was like the format, was that like an IO optimized format, or was it just a bunch of JSON? Like how do I think about that?
Oh, actually, I didn't measure that part. I can ignore that part. I didn't put that in the time. I mean, in the timetable. Actually, here I wrote really means. Oh, actually, no, sorry. I'm sure say because I'm using NFS for the storage. So that we don't need to do explicitly transfer data. The data is already in NFS.
Just want to mention that Leo has a good point, and we also offer, AWS has this thing called Lustre, so you can actually have Lustre that will be much faster. So EFS is generally it's mountable on all machines, but it's not as performant.
Yes, I agree. I mean,
Yeah.
ideally we should set up those kind of distributed file system for very fast I/O. Yeah, we didn't use that part.
I think that's all the time we have for Da's presentation. And thank you, Da, for the great presentation. So if you want to reach out to him, he is available on Slack, and just reach out to him directly. And next we have Carl Young from Emory University, and he's going to talk to us about GNN federated learning.
Okay, hello everyone. Thanks for the invitation. I'm Carl Yang. I'm going to talk about some new trends and results on graph-federated learning. And please feel free to interrupt, since I got the message that this will be a pretty casual like talk. So let's first look at this like outline. So I will first introduce a few like settings for the graph federated learning, which is a little bit different from just the distributed graph learning that I was talking about. And I will then introduce a framework called FedGraphNN, which is like a unified framework that is supposed to handle all of these different settings. Although we will see soon, like there are some unique challenges in each of these settings. So the FedGraphNN is more like a benchmark, which provides some data sets and the baselines for the different settings. And then I will focus on our two recent projects, focusing on the different unique problems in graph federated learning. And finally, I will conclude with some discussion on the future directions. So here are the few settings of graph federated learning. And the first one is distributed graphs. So in this setting, we naturally have some graphs distributed in like different clients or different local servers. So one example here is for the some research institutions which do like a drug discovery, like a molecular trial, etc. So each of them can have some valid graphs, like maybe useful for some specific diseases, or it's just valid like moleculars, right? So in the end, maybe we want to leverage the like different graphs from the multiple like institutions, but these institutions cannot really share the data directly because they have like a privacy concerns, like this regulatory restrictions, commercial competitions, etc. So that prevent them from directly share the data. And the second setting is like a distributed subgraph. So like subgraph is like a graph, like a subset of a larger graph, right? So in this setting, like one of the examples we think of is like a big like social network or a big like a recommendation system, right? So we have a lot of users or some other things like the items, but in the end, maybe some of these users and items, their interaction data will be stored in like some of the departments. So if you consider like a vertical recommendation, maybe in Amazon, you like they sell like different things, but each department or each category like maybe include some of the like the stores, like the sellers, and then they will basically have interaction data of a particular set of users, right? So they basically construct like a subgraph of a larger like a global graph, and then it probably is useful when you want to recommend a general thing, or you want to recommend some like new items, right? So you want to leverage all kinds of interactions, not just specific to a particular subgraph. And then in this setting, again, those departments, although they might belong to the same company, they might not be able to directly share their data. And finally, this like distributed ego graph setting, which we think is more like a sort of intuitive in that social network scenario, where each user only has access to his like or her own like a k-hop ego graph, maybe just 2 hop or even 1 hop, and then the computation is more like in the future when we try to do all kinds of like a recommendation or like predictions in local devices like the local mobile phones. Then each user's local mobile phone won't be like storing data of like of some other users they don't really know, right? So with this kind of real local data, how can we do like more like a generalizable like recommendation? How can we train like a more powerful model? And this is actually a particular example of the subgraph setting, right? But it's more like even more restricted. So these are some different settings, but in the end, we think there is a unified framework, just using just distribute the training of a single like a graph neural network. So the idea is we can like just share like each local model can like keep track of a local. So sorry, each local client can keep track of a local model, the same GNN shared among all local clients, right? And then they compute the gradients based on their own data, right? And then after they get this gradients, they can then communicate these gradients to a server. So this server only gets the gradients of a GNN, and then they can do something like average the gradients, or they can do some weighted average of the gradients, etc. They can do different kinds of control, but those are some different existing federated learning algorithms, which are general for different kinds of data, not just unique for graph data. And in that way, after they compute, they aggregate and do some process on these gradients, they can then send the gradients back to the clients, and the clients can just use this processed gradients to update their local model. So in the end, these local models are actually in the simplest setting, those local models are all the same, right? But actually the local client can also have the choice to make different kinds of use of this average gradients, and then they can have the flexibility to sort of trade off the global knowledge from other clients and their own knowledge. So these are also just some general federated learning problems. So here, because we have this unified framework of training GNNs, so specifically for the GNNs, we have formulated these two phases. The first phase is just to compute, is basically to compute the representation of each node from its local node features and the GNN parameters, right? And then we can get this local node representation. And the second phase is just to apply some pooling functions to basically compute a graph representation, or a link representation, or just directly a node representation, which can support the different downstream tasks in the local server, right? So this framework can actually be in this way, it can be applied to all kinds of graph mining tasks and all different kinds of graph partitions we just talked about. And then in this system, we supplied 36 open data sets, and we built all of them into one distributed system, which really is deployed in distributed machines. So that is supported by a system called FedML, which is developed by our collaborators in USC. So that one, we hope that this tool could be a general tool for providing the baselines and some data sets for the future research in this direction. Then when we were developing this benchmark system, what we actually want to solve as some research problems are how can we do what is basically different for the graph federated learning and the federated learning for visual and textual data, right? And we all know there are some unique challenges of graphs, such as they have different sizes, they can have different complex topological structures, and there are also more complex graphs than basic graphs, such as the heterogeneous graphs, knowledge graphs, and multiple views of links, etc. So this can actually bring a lot of unique challenges to the federated learning on graphs too. And these challenges, we basically categorized them into some also some generally interesting federated learning problems, such as the utilities of the learning algorithms, the efficiency, privacy, and so on and so forth. And today, the two works I'm going to talk about are more about the utility part. So this first work is starting this subgraph federated learning setting. And here is a motivation, the example of starting this problem. So here we have multiple hospitals, and each might hold some patient interaction data. And then this data are basically from subgraphs from a larger like patient networks, for example, in a whole city, right? And then when some disease happens, like when some like infectious diseases is onset, then maybe there's an institution which wants to like train a powerful graph neural networks on the whole like network of the city, right? Instead of just training it on some hospitals' data alone. And then this problem is these hospitals, again, they cannot just give their data to this like a third-party institution. And the main challenge here is, although there are these kinds of like non-IID distribution, like distribution shift among the clients, which are more like a general federated learning problem, the unique challenge we found here is how can we handle this cross subgraph like missing links? So there could be some like some links among these patients, some interactions among these patients, which are never captured by any of these like hospitals. So this of course depends on what are the links we consider, right? So let's just have one example. This links is between like patients who got the same disease in the same time, or they have like being in a same place for some particular time. Then this kind of links probably is not captured by any of the hospital at all, but they are across the subgraphs. And how can we sort of recover this kind of links to do like a more realistic, to really mimic like to approximate the training on the whole global graph? And the idea in this work is we want to we designed a model called a NeiGen to basically generate missing neighbors from the neighborhoods of each node. And here is just a visualization, like these red links, red dashed lines are basically the missing links. And then we think for each, so in the view of each like local network, we just want to predict these neighbors that are possibly missing into the other clients. And the particular model design is we first try to predict the number of missing neighbors, and then we predict the actual feature of these missing neighbors. And this NeiGen is trained by like simulation. So we can manually like remove some of the neighbors, just hide some of the neighbors, and then we train this NeiGen based on this hidden like ground truth neighbors, right? And then when we run this model in reality, we try to like use this NeiGen to predict like neighbors, right? And there are some details in how to train this NeiGen model, and so it can really predict the neighbors missing into the other like clients. And that part is pretty like complicated, and I won't be covering that in this talk. But you are like welcomed to take a look at that paper. So in the end, the ideal effect of NeiGen is like showing in this figure. So we want the model to be able to predict those like neighbors just as they are local, but those neighbors should have like similar features or similar interactions as if they are in the other clients, in the other client subgraph. So we did some experiments on the these few models we designed, and basically these are all the like previous three are just some baselines, and the FedSage Plus is the one we proposed to like train in a federated learning setting with the NeiGen model. And GlobalSage is like a globally trained GraphSage, so it is trained on the actual like a global graph. And this basically provides an upper bound for the FedSage Plus, because this like a global model, they don't actually have the missing links at all. And they use the same like a core, like a backbone model. So our model won't be able to really outperform this model. But we can see like we significantly improved over the baselines, and we actually get pretty close to the upper bound. So So that concludes the discussion about this work. But we can, if you have more questions, feel free to ask either now or towards the end of the talk. And here is the other talk, other work I also want to briefly talk about. So this is the graph classification setting. So it's more like in the graph fidelity learning setting, and we study the graph classification problem. And for the graph classification problem is people usually study it on different kinds of graphs, like moleculars, like bioinformatics, this kind of protein interaction graphs, or the protein structures, and like social networks, like subgraphs of communities, and also like geographic graphs of different transportation or like different kinds of real world networks. And a question we'll ask here is, can we learn, like can those real world networks from like different sources like benefit the learning of like graph neural networks on each of them? So why we want to ask this question is because we see like the graphs, although they can be from different sources, they can often share some similar properties or some similar like patterns, structures. Right? So these are real examples of a graph, like of moleculars, protein interaction, social networks. And then we did some more systematic like quantitative analysis to show like to basically test some of the properties, some of the commonly concerned graph properties in these different kinds of networks. And we find that some of the networks do share like similar properties. So that motivates us to do like fidelity learning to basically collaborate through even across like different fields, different domains. And here is also a natural like observation, which is when you consider like when you put like basically heterogeneous graphs together, like the graph, if the graphs are somehow different from your, like if the two sets of graphs are somehow different but not too different, that is the place where your model got the most improvements by just training on two like slightly different but not too different tasks. Right, two different data sets. So that basically says the careful handling of the heterogeneity is very like important. So based on this intuition, we then designed a model called like a graph cluster fidelity learning. So the idea is we want to again use a graph neural network to model the to do the graph classification task, but we want to cluster the clients into some like local clusters. So we try to train we share or we jointly train the graph neural networks only among the clusters which are sort of heterogeneous but not too like different, right? So that is a basic idea. And the graph neural networks we are using is called a GENE, and that is not this bottled GENE but the graph isomorphism network. And that's why basically we use this because it has some like theoretical like properties which basically says this model will be sensitive to the graph structures and node features it models, right? So so that we can use these gradients to do the dynamic clustering of the clients. And then we have this algorithm to do the dynamic clustering. So the idea is also pretty straightforward, is to just train a general fidelity learning algorithm, starting with all of the clients put together, right? And then after we reach some point, basically this first criteria means if the average of the gradients become somehow large, meaning the whole model is somehow, the model trained on all of these clients is somehow converged. And then in this case, if there are some like clients whose like gradients are still pretty large, like this, basically this second criteria, that means some of the clients didn't converge when most clients converge. So that means this particular, some of the clients could be pretty heterogeneous from the other clients, right? So in this case, we will then compute like a clustering algorithm on all of the clients based on their gradients. So on the gradients of the gene algorithm, the gene model, right? And then we perform like a bi-cluster to do the clustering. So, and after we do that clustering, we will continue this process over and over again until we reach like a stable set of clusters. And then there is basically a single model shared on one cluster, right? Federatively trained on one cluster. So there will, in the end, there will be multiple models. But the idea is these multiple models achieve some kind of a good trade-off between the heterogeneity and the performance. And finally, we did some experiments on a lot of real-world data sets from different domains. And here are some different settings, results of the different settings. The first one is a single data set setting. So we basically split a single data set into a lot of clients. And then we test how many clients we can improve, and on average, how much we can improve, right? Using the different algorithms. So GCFL is the one we just talked about, and GCFL plus is the one with some further design to stabilize the training. So we got pretty good improvements by using the GCFL algorithm, and also further improvements by using the stabilization. And this is a multi-dataset setting where we actually observe more improvements. It's basically each client has one has networks from one particular domain. And in this setting, we can see basically similar trends, but actually even slightly larger gains compared with a single dataset setting. And finally, there is a study on how we are able to reduce the heterogeneity by doing the clustering. So the feature heterogeneity and the structure heterogeneity. So the dashed lines are the original values, and these new lines are new bars are basically the per cluster heterogeneity after we do the clustering. Right? So the algorithm, by using the gradients of the gene model, is actually able to really reduce the heterogeneity or the average heterogeneity in most of the cases. So that concludes the discussion on the second talk, second work. And here is my conclusion of today's talk. So we did some very pioneering work on graph-federated learning, and we find the pretty promising but improvable results, and as well as the techniques. And then we think there are actually a lot of open questions to be studied. Even on the utility part, there could be many new GNN models and federated learning algorithms to be studied. And the efficiency and privacy part, we are collaborating with a lot of people to try to discover the.
It's ready for the practice. Why is it 5?
Okay, so finally, we think there are I also marked some of our recent works which could be applied for the efficiency and privacy study, but they are actually not studied yet, not even by one work for the graph-federated learning setting. And finally, there are some collaborations we would like to explore, with Amazon and with DGL. So thank you for attending the talk, and I will really welcome you to follow up, because this is a emerging new domain, and we do want to foster an active community around it. Thank you. And any questions?
Thank you, Carl. I do have a question. How large are the data sets that you're currently working with?
Yeah,
And also,
so-
what's the general penalty we're expected to have for much larger data sets?
Yeah, that's a very valid question. I think I used to have that slides about the size of the
Okay.
data. Yeah, but I just removed it because it's shortened. Yeah, but to answer that, the most of the data sets, like the Quora size here, PubMed, maybe they are just thousands of nodes, like the Euro, like a benchmark for graph. And the MS Academia is actually a little bit larger. But I remember it's just also tens of thousands. So these graphs are pretty small still. So the study on it is mostly on the effectiveness, the utility of the algorithm. We haven't really touched like the boundary on how much like the data, how large the graph we can handle right now. But that is a very valid thing to consider next.
Actually, so just putting that in context, so like if we're working with, let's say, the VA in the US, which might have hundreds of thousands of patients and a lot of EHRs, like then this work would be, we would need to subset on like maybe like 1,000 cancer patients or something like that, and
Yeah.
it would be maybe in scope for that, or maybe one cancer patient but their full history. Like I'm just wondering how you contextualize it with just the current state of the art.
Yeah, you are still asking about the size of the data, right?
Yeah, like imagine we're dealing like a knowledge graph mining problem. Just I'm trying to get a sense of it.
Yeah. This model by itself is pretty like not scalable yet. So we only consider like the number M is like the number of clients here. So firstly, the number of clients is still pretty small, and then because the number of clients is small, then the communication is not really a big deal here. So we do have like the computation efficiency curve, and we can see our model does incur some additional communication, which is actually pretty concerning. But because the clients are not a large number of clients, that is not a problem yet. And then because every graph is pretty small, we can actually put the whole agency matrix into memory and even into GPU memory. So we don't have like the problem of like the actual like distributed learning problem at all. So right now, but of course, I think these are very different directions, right? We focus on the algorithms while like DGL team focus more on the scalability. That's why like there could be a lot of spaces to collaborate.
Absolutely. I have another question regarding work on differential privacy on graph, graph databases, or just simply graph. Is there any related work that you can point us to?
Yeah, we did have a work like this one.
Yeah, I'm looking at that.
Yeah, this one is like studying the link privacy. So we want to generate new graphs, and we want this new graphs. So we want to use these new graphs to do like downstream analysis, but in the same time, we don't want people to infer like links from these new graphs. So infer the original links from this generated graphs. So that is the setting, and it's not related to federated learning at all, but it could be like a valid thing to consider in the federated learning setting.
Right. Cool. Any other questions? Okay, great. I'd like to thank our speakers. Da, I think he just left, and also Carl, thank you so much for the great presentation. And this is really, like you said, it's the forefront of federated learning. It's a cutting edge research. So we'd definitely love to collaborate, and we'll encourage everyone in the community to reach out to Carl. And he is also now on Slack channel. So Until next time, we'll say goodbye for now. And just a reminder, we are going to have our meeting. We're not going to have one in November, but we will have one for December 11th, which is also a Thursday of the following month. December 11th is going to be our next meeting. And if you have any question, of course, we'll send out reminders to make sure that everyone has the right date. And again, I want to thank everybody for participating. Any other questions?
Yeah, thank you.
YouTube.
Yeah.
Yeah, thank you, Carl. So I see a question from Maxwell. Yes, we will record this meeting is recorded, and I will be putting that on YouTube. So just go to the Slack channel, and I will upload it today. Yeah.
Great. Yeah, I just want to say one thing, like at the end, like as a small advertisement. So we are trying to like organize the first workshop for graph fidelity learning in the iClear 2022 conference next April. So if anyone will be interested, we really welcome you to submit a paper to attend the workshop, etc. Thank you.
And Carol, you can also advertise in the Slack channel. You can just put a note there saying that you are looking for participation from the iClear conference. Feel free to put that in the general window.
Okay.
Yeah, so that's perfectly fine.
Sounds
And for
great.
the yeah, of course. For those of you who don't have a invitation from the Slack channel, what I'm going to do is I'm going to send you an invitation link. And I'm copying that right now. And I'll put that back in the Slack channel. Yeah, too many windows open, sorry. So let me, okay, so I'll put that in the chat window here. I'm gonna send that to everyone, and here you go. Oh, I have a problem copying the link there. So I'll do it again. Okay, second time's the charm. Okay, so if you have not joined the Slack channel, here's the link in the chat window. So feel free to join. And with that, we'll conclude this workshop, and I'll stop the recording now. Feel free to socialize and continue to hang out and ask questions, and I'll be around for the next 10 minutes.